everyone, thank you so much for clicking onto the video. Today's learning objectives are all to do with the addition reactions of alkenes. So we're going to be looking at the electrophilic addition reactions of alkenes with hydrogen bromide, sulphuric acid and bromine. And we're also going to use the use of bromine to test for unsaturation. And we're also going to look at the formation of major and minor products in addition reactions of unsymmetrical alkenes. And by the end, we should be able to outline the mechanisms for these reactions and explain the formation of major and minor products by reference to the relative stabilities of primary, secondary and tertiary carbocation intermediates. Now we're going to look at the reaction of alkenes with bromine or any other halogen. So first we need to learn what an electrophile is. So an electrophile is an attacking group with a vacancy for a pair of electrons, and a new covalent bond results when the vacancy is filled. And they can be positively charged, so for example H plus or bromine plus. The double bonds in alkenes are areas with really high electron density, and this attracts electrophiles because the electrophiles are basically looking for electrons. And so the alkenes undergo addition reactions. In particular, they undergo electrophilic addition reactions, and we're going to see that now. So the reagent we're going to be using is bromine, and we're going to be using room temperature conditions. So we're going to have a look at a mechanism of this reaction. Ethene and bromine going to form 1,2-dibromoethane. So we start off by drawing the ethene molecule. So we have a carbon double bonded to another carbon, and then the hydrogens. Then now I'm going to draw in a bromine. And so what happens is that as this bromine molecule moves towards the alkene, the pi bond electrons of this double bond repel the electron pair in the bromine bond, because we know that covalent bonds are just a pair of electrons. And so this induces a dipole, and this bromine molecule becomes polar, and also it becomes electrophilic. So what we get is that the top bromine will get a partially positive charge, and the bottom bromine will get a partially negative charge, because basically it moves towards the alkene where the double bond has very high electron density. So this repels any of the electrons that were originally around the top bromine, and they will all be collected around down where the bottom bromine is. And so this is how we get the partial charges. And so the mechanism looks like this. So these two electrons from this bond go towards this partially positive bromine, the partial positive charge. And then these two electrons from this bond move towards the bottom bromine. And what this forms is an intermediate that looks like this. So we have these carbons and then the hydrogen. So now the double bond has gone because the two electrons have gone to this partially positive bromine. And so we've formed a bond with bromine, and everything else is the same, except for we don't have the double bond. And now the carbon is positively charged because it's lost some electrons due to losing that double bond. And we also form the bromide ion, because we've lost, this is basically the bottom bromine atom of the bromine molecule. And because the electrons from the covalent bond have moved towards it, it's become a bromide ion. And this intermediate is what we call a carbocation. And it's positively charged. So now what we form is the the bromide then attacks this carbon with a positive charge because it's attracted to it because electrons are negatively charged. And so what we form is this 1,2-dibromoethane. And so this is an electrophilic addition reaction. And this is because the attacking group is an electrophile. So the electrophile in this case would be the bromine with the partially positive charge in bromine. And it's an addition reaction because we are adding bromine across the double bond. Now we're going to look at the reaction of alkenes with hydrogen bromide. So we can react alkenes with hydrogen chloride, hydrogen bromide, and hydrogen iodide to form a haloalkane. And so for this example, we're going to look at the reagent of hydrogen bromide. And the thing that's acting as an electrophile is the hydrogen with a partially positive charge in hydrogen bromide. And we're going to look at ethene and its reaction with hydrogen bromide to form bromoethane. So first we draw out ethene, so carbon double bond and then the 4 hydrogens. And now we draw out the electrophile. And because there's a difference in electronegativity between the hydrogen and the bromine, because the bromine is much more electronegative, that means that we get some partial charges. So the hydrogen gets a partially positive charge and the bromine gets a partially negative charge. And so because the double bond of the ethene is an area of really high electron density, that means that the electrophile is attracted to this double bond. And what happens is that these 2 electrons from this bond move to the hydrogen with the partially positive charge. And then these 2 electrons from this double bond then move to the bromine. And what we get is that we get the positive carbocation forming again. So we'd have a carbon. So this carbon on the left would now be attached to 3 hydrogens instead of 2. And then the double bond will have now become a single bond. And then this carbon will only have 2 hydrogens attached. And it'll be positively charged because we've just lost some electrons. And also bromide, the ion is formed because the electrons from the original HBr bond have moved towards the bromine and so made it into a negative ion. And this negative ion has a lone pair of electrons, and so it attacks the positive carbocation because the carbon is positive. And so what happens is that these 2 electrons then attack this carbon, and then we form this bromoethane that we're after. And the carbon is no longer positively charged now. So this is bromoethane. And this is actually the only possible product because no matter how we do it, because there's only 2 carbons, like if we flipped it around, so if the bromine was attached to the other carbon and we flipped the molecule around, it would look exactly the same as this. So there is only one possible product. And again, this is an electrophilic addition reaction. And this is because the attacking group is an electrophile, and also we are adding the hydrogen bromide across the double bond. Now we're going to look at the test for unsaturation. So in order to test for unsaturation, which is just a carbon-carbon double bond, we can add bromine water to a sample and it decolorizes in the presence of a double bond. So originally, bromine water is an orange-brown kind of color, and it decolorizes in the presence of a double bond. It can be used quantitatively to show the presence of multiple double bonds in compounds like polyunsaturated oils. And we can also use bromine water to identify between an alkane and an alkene, because alkenes have the signature carbon-carbon double bond, whereas alkanes only have carbon-carbon single bonds. And so if we were looking at this experiment, I would say that the one on the left would be the alkene because it's decolorized. So this would be the alkene. And the one on the right would be the alkane because the bromine water has stayed orange-brown. And the key thing to remember about these sorts of questions that you might get asked is that when they ask you for your observations, you have to put down what it started off with and what it looks like now. So if they asked you what happens to, what would you see if you added bromine water to an alkene, you'd have to say that the orange-brown colour of the bromine water will decolorize. Now we're going to have a look at the reaction of propene with hydrogen bromide. So with some addition reactions, so for example with propene, there isn't just one possible product which is formed. And so we have to decide which product is the major product sometimes. And so for this example, we actually have two possible reactions. The first is if we add the hydrogen onto the middle carbon and then the bromine onto the last carbon. And the second reaction is if we add the hydrogen onto the last carbon and the bromine onto the middle carbon. So now we're going to have a look at their mechanisms. So for the first reaction, we have propene. So I'm just going to draw up propene centered around the carbon-carbon double bond. And now we're going to draw hydrogen bromide, like we do usually, and give the charges as well. And again, they have charges because there's an electronegativity difference between hydrogen and bromine. And so hydrogen gets this partially positive charge because the power of bromine to attract the electrons in that covalent bond is much stronger. And so all the electrons are basically crowded around the bromine instead of the hydrogen. And so this hydrogen with the partially positive charge then becomes an electrophile. So it's attracted to the high electron density of this carbon-carbon double bond. And so again, what happens is that the two electrons from this double bond, well, one of the bonds, then moves to this partially positive charge of the hydrogen. And then these two electrons from this covalent bond move towards the bromine. And what we form is a carbocation. So I'm going to draw it out this time. So I'm going to start out with the CH3. So we have CH3. And now we have a carbon which was part of the double bond. And then now I would have drawn a double bond, but now it's become a single bond. So this is the newly formed single bond. And then we have one hydrogen, and I'm going to add the hydrogen from the hydrogen bromine to this carbon. And so this last carbon then only has two hydrogens. And so it gets a positive charge because we've just lost some electrons. And also the bromide ion, is formed because the electrons from that HBr covalent bond have moved towards the bromine, making it negatively charged. And so now what happens is that the two electrons, the lone pair of electrons on this bromide ion, are then very attracted to this positive carbon, and so forms a bond with it. And so we form CH3, CH2, and we've got carbon with the two H's, and then now also the bromine is attached, and this molecule is 1-bromopropane because the longest chain is 3 carbons, so it's just a straight chain, and bromine is attached to the first carbon because it wants the lowest number, so it can't be the third carbon. But there's actually another reaction that we can get, which forms a different product. So now we're going to look at the mechanism of this second reaction. So again, we start off with the same thing. So we have a carbon-carbon double bond, hydrogen, CH3, another hydrogen, and another hydrogen. Then again, we draw the hydrogen bromide and put in the partially positive and partially negative charges. And then again, the electrons from this bond then move towards the partially positive charge of the hydrogen. And then these electrons then move towards the bromine because of some repulsion from the incoming electrons from that double bond. And then we form a carbocation again. But this time I'm going to add the hydrogen onto the last carbon instead of the second carbon. And so again, we have the CH3. So right now I'm drawing this group. This is the CH3 group. And then I'm going to have the first carbon of that was attached to the double bond. And I'm going to put a hydrogen on it, but I'm not going to attach the hydrogen onto this carbon this time. And now we have the newly single bond, and then another carbon and two hydrogens. And now I'm going to attach the hydrogen from the hydrogen bromide onto this carbon instead. And so now this middle carbon will have the positive charge because it's lost the electrons. And again, we have bromide forming. And so the same thing happens. So these two electrons are attracted to the positive charge of the carbon. And so we form another type of bromopropane. So we have CH3, CH, but this time we have the Br on this carbon, and then CH3. And this is 2-bromopropane because the bromine is on the second carbon. And so now we have to look at which one is the major product. If we go back to the first reaction, there's something really important that we need to have a look at. So the carbocation which is formed is actually what we call a primary carbocation. And that's because on this carbon with the positive charge, there's only one alkyl group attached to it because the other two things are hydrogens and they're not alkyl groups. And so we call this a positive carbocation. And this is really important to remember. And then for the second reaction, if we have a look at this carbocation, so this carbocation on the carbon with the positive charge, we have two alkyl groups attached. So we have one here and one here. And so therefore, we call this a secondary carbocation. And it's the difference in these carbocations that actually determine which product is formed majorly. Now we're going to talk about the positive inductive effect. So we've seen that in the reaction between propene and hydrogen bromide, we can form two possible products. And now we're going to discuss how we determine which one is formed majorly, so which one we have more in the products. And so firstly, we need to look at the different types of carbocation. So I kind of introduced this idea before, but we're going to look more in detail now. So on the left, we have a primary carbocation. And what that is that we have one alkyl group attached to the carbon with a positive charge. So the alkyl groups are all the R's. So this here is an alkyl group. And then a secondary carbocation is where two alkyl groups are attached to the carbon with a positive charge. And a tertiary carbocation is where we have three alkyl groups attached to this carbon with a positive charge. And what the positive inductive effect is that it states that alkyl groups will release electrons onto the carbon with a positive charge. And so therefore what we get is we get some electrons going towards the carbon where all the alkyls are. And what this does is it makes this carbon with a positive charge a lot more stable, and so it forms, and so that carbocation is more stable. And so from this we can see that the tertiary carbocation is the most stable because we have more alkyl groups which are releasing electrons onto this carbon with a positive charge. And so thing to remember is that by the positive and inductive effect, electrons are released onto the carbon with the positive charge by alkyl groups. And what this does is it makes the charge more stable. So it makes this carbon with the positive charge more stable, and in turn that means that the carbocation is more stable. And we can also call this carbocation an intermediate because we form this in the middle of the reaction to form and before we form the product. And so the carbocation is more stable. And now we need to know the general rule. So the general rule is that the major product is formed from the most stable carbocation. So first of all, we can say that the most stable carbocation would then be a tertiary carbocation because we've got 3 alkyl groups. So the most stable carbocation would be the tertiary carbocation, as we have 3 of these alkyl groups which release electrons. And so now we need to say about the actual effect of this. So what we have is that the major product, so this is the main thing you need to remember here, is that the major product is formed from the most stable carbocation. And so looking back at our example with propene and hydrogen bromide, what we had was we had 2 products. We had one bromopropane, so CH3, CH2, CH2Br, and we also had 2 bromopropanes, so with the bromine on the second carbon this time. And so one bromopropane was formed from a primary carbocation because we would have formed it from this carbocation. Because the positive charge of the carbon would have been on the carbon where the bromine is attached to now. And so because we've only got one alkyl group here, this is a primary carbocation. Now looking at the second product that we formed, this 2-bromopropane, we formed this from a secondary carbocation because we formed it from CH3, CH, and then CH3. Because again, the positive carbon is where the bromine is attached to now, because that was the last step of the addition reaction. And so this is a secondary carbocation because on this positive carbon we've got one methyl group and another methyl group. So that means we have two alkyl groups. And so this is a secondary carbocation. And we know that the secondary carbocation is much more stable than the primary carbocation, because there's two alkyl groups releasing electrons onto this positive charge, whereas for the primary carbocation we only have one alkyl group releasing electrons onto the positive charge of the carbon. And so this means that for the reaction between propene and hydrogen bromide, the major product will be this 2-bromopropane. So we have that the secondary carbocation is more stable than the primary carbocation, and because the major product is formed from the most stable carbocation, that means that 2-bromopropane is the major product. If we did have a reaction where we formed a tertiary carbocation, then of course the product that was formed from that tertiary carbocation would be the major product. But in this case, we only form primary and secondary carbocations. So our most stable carbocation would be the secondary. Now we're going to look at the reaction of alkenes with sulphuric acid. So concentrated sulphuric acid will also add across the double bond, and this reaction is exothermic and occurs at room temperature. So the reagent we're using is concentrated sulphuric acid, and the electrophile is the hydrogen with a delta positive on this H2SO4 structure. So if I draw out the structure of H2SO4, we can kind of see more as to how this hydrogen gets this partially positive charge. So we have So this is the structure of H2SO4, so sulphuric acid. And what you need to see is that there's an electronegativity difference between the oxygens and the hydrogens, because oxygen is much more electronegative, and so the power for it to attract the electrons in the covalent bond between the oxygen and the hydrogen is much stronger. And so we get more electrons crowded around the oxygens compared to the hydrogens. And so the oxygens obtain this partially negative charge. And this means that the hydrogens have partially positive charges. And so this is what the hydrogens are what we're going to use as electrophiles for this reaction with ethene. So now I'm going to start drawing the mechanism of the reaction between ethene and sulphuric acid. So we start off with ethene, and this is C2H4. And then now I draw the sulphuric acid, and we're forming this compound called ethyl hydrogen sulfate. So I draw the H2SO4, and we tend to draw the whole thing out. So we tend to draw HO and then sulfur double bonded to two oxygens, and then another oxygen and a hydrogen. So this is our H2SO4. And then we draw in the partial charges of the hydrogen and the oxygen, which are nearest to the double bond. And so again, the partially positive hydrogen is attracted to the high electron density of the double bond. And so what happens is that the electrons from this bond then move to the partially positive charge of the hydrogen. And then these two electrons from this covalent bond then move towards this oxygen. And so what we get forming is another carbocation. So we form CH3, CH2, and then this CH2 will be positive charged now because it's lost some electrons. And then we also form the rest of what was the H2SO4, but now as a negative ion because it's lost the H+. And now what happens is exactly the same as for all the other electrophilic addition reactions. We get these two electrons which are attracted to this positive carbon and so forms a bond. And so what we form is this ethyl hydrogen sulfate, which is CH3, CH2, O, S, and then double bond O, another double bond O, OH. And so this is ethyl hydrogen sulfate. So you probably won't guess. So you probably won't get asked how to name that. And actually, a thing that you might need to know is that if you add water to this ethyl hydrogen sulfate, we get an alcohol, and the sulphuric acid is regenerated. So we get this equation. So we have if we add water to the product, we get CH3, CH2, OSO3H, and then if we add water, we get CH3, CH2, OH, and so we get ethanol, and then sulphuric acid is reformed. And so this used to be a method where they formed an alcohol from an alkene, because we originally started with ethene, and we've managed to end up with this ethanol. However, now they've found other ways to form ethanol or different alcohols, and so we'll be looking at that in the topic of alcohols. And again, looking at the mechanism, this is an electrophilic addition reaction. And this is because the attacking group is an electrophile, so it's the hydrogen which is partially positive, which is part of the sulphuric acid, and it's an addition reaction because we're adding the sulphuric acid across the double bond. Now we're going to have a look at some questions. So for question 1, methyl propene reacts with hydrogen bromide to produce 2-bromo 2-methyl propane as the major product. For A, name and outline the mechanism for this reaction. So with alkenes, we have an area of very high electron density where the double bond is, and so it attracts electrophiles. And these electrophiles get added to the alkenes, and so these kinds of reactions are called electrophilic additions. So for A, we have an electrophilic addition. And so we're starting off with methyl propene, so that's 3 carbons in the main chain, and then a methyl. Now the methyl doesn't have a number because we know where it goes, because it can't go on the 2 end carbons, because otherwise we would make butane, and so it must be on this middle carbon. And we also have propene, so we have a double bond where the first carbon is, because if we flip it the other way around, it'd still be the same. And so this is what we start off with. And now we draw the electrophile. So we have hydrogen bromide, and the hydrogen and bromine both have partial charges because the bromine is much more electronegative. So there's a big electronegativity difference between hydrogen and bromine, and so the bromine obtains a partially negative charge, whereas hydrogen will get a partially positive charge. And that's because the electron density is all around the bromine and not very much around hydrogen. And this means that because the double bond is an area of high electron density, these electrons are attracted to this partially positive hydrogen. And so they move towards this partial charge, and then the electrons from this covalent bond between hydrogen and bromine then move towards the bromine. And so what we form is a carbocation. So we have CH3, and then we have CH3, and now we've broken the double bond, and we have carbon and the two hydrogens, and now we attach the hydrogen to this carbon because it's formed a bond with it. And so this carbon in the middle now has a positive charge because we've lost some electrons. And what's also formed is a Br minus ion because the two electrons in that hydrogen-bromine bond have moved towards the bromine, making it negative. And so now what happens is that we get these two electrons from the bromine attracted to the positive charge on the middle carbon. And so they move to this positive charge, and we form CH3, C, Br, and then CH3, and then the CH3. And what we formed is 2-bromo, 2-methyl propane. And this is because the methyl group and the bromine are both on the second carbon. And so this is our mechanism for the reaction. For B, draw the structure of another product of this reaction and explain why it's formed in smaller amounts. So we need to remember that with these electrophilic addition reactions, depending on which carbocation we form, we can sometimes get more than one product. So the other product would be formed if the hydrogen attached itself to the middle carbon instead of the outer carbon. And so the positive charge would then be on the last carbon. So if I draw out the carbocation, so if the hydrogen from the hydrogen bromide attached itself to this carbon and then broke the double bond, and we only had two hydrogens on this last carbon, this would then have the positive charge. And so the bromide ion would then be attracted to this positive charge on the carbon, and this time we would form something a bit different. So what we form this time is 1-bromo, 2-methyl propane. And now what we need to look at are the carbocations to explain why we get the major product being 2-bromo, 2-methyl propane instead of this 1-bromo, 2-methyl propane. So we've learnt that looking at carbocations, we have primary carbocations, secondary, and tertiary. So primary ones look like this. They have the carbon, and then with the positive charge, and then they have one alkyl group and then two hydrogens. And then the secondary, so this is the primary, and then secondary we have the carbon with the positive charge, and then two of these alkyl groups, and then a hydrogen, and this is the secondary. And then for the tertiary, we have the carbon with the positive charge, and then three of these alkyl groups attached to it. And we know that because the electrons are released onto the carbon, it stabilizes the carbon, and so therefore the tertiary carbocation will be the most stable because there are more alkyl groups to release electrons onto this carbon with a positive charge. And so we have that the tertiary carbocation is the most stable, and then also the primary carbocation is the least stable. And so another thing that we know is that the major product is formed from the most stable carbocation. So this is the most important thing to take away, is that the major product is formed from the most stable carbocation. And so if we look back at our example, so we had a carbocation that looked like this. We had the methyl group, and then we had a positive charge on the carbon, and the other one we had was if we had the positive charge at the end, and this time the positive charge would be on the carbon at the end. And so we can see that the first one I've drawn is a tertiary carbocation, because on this carbon with a positive charge we've got one alkyl group, the second alkyl group, and a third alkyl group. Whereas on the second carbocation I've drawn, this is a primary carbocation, because we only have one alkyl group and two hydrogens. And so this is a primary carbocation. And here we have a secondary, a tertiary, sorry. And so that means that the major product will be formed from the tertiary carbocation. And the major product is this 2-methyl 2-bromo propane. Before I start on the second question, feel free to click off the video and try it for yourself first. So we have that propene reacts with bromine by a mechanism known as electrophilic addition. For A, explain what is meant by the term electrophile and by the term addition. So the definition of an electrophile is a species that has a vacancy for a pair of electrons. To form a covalent bond. And we also know that they can be positively charged. So for example, we could have a H+. And so this is for an electrophile. And then for addition, what we mean by addition is that it's when we add something to a molecule. And so for this example, we're adding bromine across the double bond. So for B, outline the mechanism for the electrophilic addition of bromine to propene and give the name of the product formed. So we have propene. This should be a double bond. And then we have bromine. And the Br with the positive with the partially positive charge is actually the electrophile. So we have bromine, and the top bromine will have a delta positive charge, and the bottom will have a delta negative charge. And this is because when it moves towards this double bond, the electrons from the double bond, as it's a very high area of electron density, it will repel the electrons already onto the upper bromine. And so the electrons tend to gather around the bottom bromine, and so that develops a partial negative charge, whilst the top bromine will have a partially positive charge. And then what happens is that the electrons from the double bond are then attracted to this partially positive bromine. And so it will form a bond, and then we have the two electrons from this covalent bond moving towards the bottom bromine and removing it because of the incoming electrons repelling them. And so what we form is we form a carbocation. So we have carbon and then a hydrogen, and then this will be a bromine, and this carbon will be positively charged. We also have a bromide ion that we formed because the electrons from the original bromine bond have moved towards this bottom bromine, making it negatively charged. And so now what happens is that we get these two electrons from the bromide are attracted to this positive carbon. And so we form CH3, CH, Br, and then CH2, Br. And how we name this is that we first look at the longest carbon chain, which is 3, so it's some kind of propane, and then we label the carbons. So we have 1, 2, and 3, or we can label them 1, 2, and 3. And then the halogens need to have the lowest numbers, and so we have to take the bottom numbering system because they would land on carbon 1 and carbon 2, compared to if we took the top numbers, then they would land on carbon 2 and carbon 3. So we have to use the bottom numbers. And so we get 1, 2, dibromo. So you have to remember, firstly, to use both numbers. So you have to state the 1 and a 2. And then we also have to use the prefix di, meaning 2. And then bromo, propane. And we see that there's only one product formed here because no matter where we put, whichever carbocation we make, we could make this one. So we have CH3, CHBr, and then if we have the positive carbon on the end, it would actually make the same molecule. It'll still make 1,2-dibromopropane. So that's why we only get one molecule.